Hey, so we're continuing to look at some more functions, specifically exponential and logarithmic functions. And while I talk about sinusoidal functions in the notes here, I'm not going to go through any examples of those, as well as something new, these logistic functions. So a variety of new things. First, I have a graph here showing the radioactive decay of an isotope, and you can see a couple points from here, and we want to create a model using this base of E. And so first of all, one thing to keep in mind is that this here, that represents the rate of growth or decay. This is Greek letter lambda, but that value there represents the rate of growth or decay. If something is in decay like this, that should be a negative number. If it's growth, it should be a positive number, and any exponential function can be expressed in this form. And when we start looking into ideas of calculus, expressing exponential functions with a base of E becomes quite helpful. And so to come up with an equation, what do I know? Well, I know at time 0, the amount is 10. So I can take this and say the amount, if I just go to this general form, A naught E lambda T, well, I know at time 0, so when time is 0, the amount is 10. Which means all of this right here is 1, because anything to the power of 0 is 1, which means A naught must be 10, which makes sense because that's kind of what A naught means. And so quite often we can skip all that and just get straight to this. I know, and a little more generally, the amount at any given time is going to be 10 times E to lambda T. Okay, still don't know what lambda is, still don't know what the rate of decay is, but we can really just jump to this. That's it. I also know another point. I know after 30 days, there's 3.15 grams remaining of this. So let's utilize that. I can say the amount, so it's going to be 3.15 equals the initial amount times E to the power of lambda times time, which is 30. And now here we can solve for lambda. And in this case, solving it algebraically is quite quick. Divide both sides by 10, you get 0.315 equals E to the 30 times lambda. Put this in logarithmic form. This is the same as the natural logarithm of 0.315 equals 30 times lambda, which means lambda must equal the natural logarithm of 0.315 divided by 30. All right, now that said, that's the three significant figures. That's approximately negative 0.0385. That's my approximation. Notice it's a negative number. You can also imagine this meaning that 0.0385, similar to 0.385% rate of loss of decay. However, now I have my equation, so now I can say my equation here in general, I don't know, maybe I'll put it right here, is 10, actually I should say this is approximately because this is rounded. So my approximate equation is 10 to the power of E negative 0.0385 times time. Right, that's my equation, accurate, to my approximate equation here. And so if I want to find the half-life, I have a few options. I can solve this graphically, and maybe I'll just mention quickly. Half-life is for how long it takes for have half the amount left. So if we start at 10, I can see visually right here, it's got to be a little bit less than 20 days. So one idea, if I want to be more accurate, is I could just go to a graphing device, graph the function I have. Let me adjust my window settings here. There we go. There's my graph of my function that I determined. Here's where it equals 5, and I get approximately 18 days. That's that's a graphical approach, which is great, but also it's actually pretty nice to get this done algebraically, so I'll, for this, show it algebraically. So the half-life would be when this amount here is 5. So when 5 equals 10 times E to the negative 0.0385 T. Divide both sides by 10, you get 1/2, which makes sense. It's half-life equals E to the negative 0.0385 T. I'm running out of space here. Put this into logarithmic form. You get the natural logarithm of 1/2 equals negative 0.0385 T. Divide both sides by that negative 0.385 T, and you get the time, the half-life, is approximately ln of 1/2 divided by this decimal, which, if you go to your calculator, you should get approximately 18 days, which I already saw graphically. In this case, just be aware of how to do both. Algebraically, we are expected in an HL course to know how to get to that value algebraically. All right. Here I have some data on the cumulative box office revenue. That means the amount of revenue in total up to that point in time for Avengers Endgame in United States. This all being American dollars. And so, for example, that there represents after 4 weeks of release in total, there was $781 million in revenue. And that's everything it made up to that point added up together, so the cumulative amount. So I want to create a regression model for this first, and I have to think what's an appropriate model for this. And in general, anytime we have a function that increases quickly at first and then slows down, that's what we see here. It jumps up, from 0 to 474, but then it's slowing down. We have some sort of growth like this. Something like this, a logarithmic model is always quite appropriate. So I want to use logarithmic regression, which actually it's going to be in terms of the natural logarithm. And so now you want to be familiar with your GDC. But you should get something, y is approximately, y being the revenue, you should get approximately this. This is to 3 significant figures. 485 plus 225 times the natural logarithm of x. Keep in mind, the value that I have on my GDC when I come up with this is more accurate, and if I want to work with this, I should use that value there. All right, so now I want to use this to determine not the cumulative amount in the 5th week, just how much that the revenue was in the 5th week of release, which means I want to figure out what goes here, whatever the number that is, which I can do quite quickly with this equation, and then subtract these two values. Because if I just find this value here, that tells me the cumulative amount. And so to find the 5th week of release, I just want to let x equal 5. And so y will be approximately 485 plus 225 times the natural logarithm of 5. Or even better, use the values that are on my calculator. And you should get about $847 million. So that's cumulative. So that 847 is not my answer. 847 is my prediction of what would go right here. 847. So if I want to find how much revenue this movie made in just its 5th week, all I need to do is take this and subtract that. That difference will tell me the revenue in that week. And so for my final step, I'll say in week 5, all I need to do is go 847, and keep in mind, well, this is now a prediction anyways, 847 minus the 781, and you get 66, so $66 million is our prediction for what its revenue was in the United States during the 5th week of its release. Right, lastly, this type of function we see here is a logistic function. And if I just kind of scroll up here a bit, logistic functions always have this behavior where they grow exponentially at first and then they slow down. And in fact, many data that grows exponentially at first, over time stops growing exponentially. For example, viruses quite often grow exponentially at first, but then after a while they slow down. There's only, there's limits to how much a virus can spread. And so they can always be expressed in this form right here, which I'll just write in the actual question. So before I even look at the specifics of this question, let me write down that in general, a logistic equation can be expressed like this. It's a function of time, L over 1 plus C, e to the negative kt. All right, so a few things to be clear about this. That L, we call that the carrying capacity, which is essentially the maximum that this function can reach. It's actually, if you look at my graph here, it's represented by a horizontal asymptote. This model will actually never reach the carrying capacity. It'll get infinitely close. And so it's essentially the maximum it can ever reach, which, if we look at this question, we're looking at a school with a population of 1,000. And so that's going to be our carrying capacity. This function, if we're looking at this virus that's spreading, can never surpass 1,000 people in the school when there's only 1,000 people in the school. And so I can take this now and just replace that L with 1,000. All right, what do we know a little more specifically? We know at first, on day 0 times 0, there were exactly 3 people infected. And 1 week later, 7 days later, 72 people have contracted this flu. So now I want to create the model from that. So looking at just time 0 is quite pleasant because at time 0, we saw this in a similar question before. When time is 0, this whole exponent for e becomes a 0, which means we have e to the power of 0, which is 1. And so anytime we have a logistic equation at time 0, all we really need to focus on is this part, because e to the power of 0 was 1. And so I can use that information. I know that in total there were 3 people sick. So this equation equals 3. The carrying capacity is 1,000. And I can now use that first fact. There was 3 people sick at time 0 to come up with this equation. And again, we'll always see this for a logistic function, that this simplified form is always true for time 0, for the beginning of it, which means I can solve for c quite easily. 1 plus c must equal 1,000 divided by 3, which means c must equal 1,000 divided by 3. Take away 1, which I'll decimalize as 332.3 repeating. Which means I know more about this equation. I know that that value of c is 332.3 repeating. So now let's look at the other point of information we know. 72 people 1 week later. And so taking this equation, I know the equation will equal 72. The carrying capacity is a constant. The c I now know is about 332.3 repeating times e to the negative. I don't know k, but I know that 72 people were sick after 1 week. So that is now a 7. And now I can solve for k here. Now this equation, you could solve this. Actually, I should make this. Excuse my messiness. There we go. You could solve this algebraically. You would use a natural logarithm at some point. It is fairly messy here, so you may prefer just to solve it graphically. Graph the left-hand side, graph the right-hand side. That's what I'm going to do. See where they intersect. And so let me just switch here. And so this here, let me adjust my settings. This is the right-hand side of the equation, y equals 72. That's the left-hand side. I need to adjust my scales to actually see that 72 and where they intersect at approximately 0.464, which is accurate to 3 significant figures. So 0.464 is my value for k. So I solved by graphing, and I got k is approximately 0.464, which means I now know my model. I'll put this all together. I can now put this all together and say f as a function of time, the number of people sick, is going to be 1,000 divided by 1 plus 332.3 repeating. I'll stick with that, times e to the negative 0.464 t. I really got to give myself more room to write here. Oh well, now that's a main part of my question done. And so now I want to use this model to predict how long it will take for 1/4 of the school's population to have contracted this strain. And so 1/4 of the school's population is going to be 1/4 of 1,000, so that's 250. So at this point, all I need to do is really essentially solve this for 250. And again, you could solve this algebraically, but I think this is a very good model definitely to solve this graphically. So I'm going to graph this equation. I'm going to graph 250, and then I'll be done. So let me turn these off. Here is the graph of my logistic model. Let me adjust my window settings here so that it's a bit more appropriate for what we're seeing here. This is showing me the growth of this flu, this virus around the school. Here's 1/4 of the school population, 250, and they intersect at just past 10 days. So approximately 10 days, we will, according to this model, 1/4 of the school's population will have contracted this flu. So again, approximately 10 days. So before I just kind of wrap up, just keep in mind these logistic models. Some of the new terminology, I'll kind of go back here now. These logistic models always behave like this, but this idea of carrying capacity, which is technically a horizontal asymptote, is that value there. Mathematically, like the equation will never actually reach it, but it is just a model, but it'll get infinitely close. And keep in mind at the beginning, at point times 0, it's always just L over 1 plus this constant C. That's enough for me.